Hello, good morning, everyone. And let's first talk about the second homework assignment I marked early last night. For question 8, part B, you are supposed to calculate A times C and B times C separately. Now, some of you only calculated AC, but not BC. And for B2, A plus B times C, I think the most convenient way or the intended method is to use the distributive law of matrix. That's AC plus BC, and then you can use the previous results. So this is the answer. For question 12, part A, this is how you prove. This is how you prove. You have to do an expansion and also to get the right-hand side exactly. Now, some students, the left I in the final expression or the left I square in the final expression, that's not exactly correct because you need to get the right-hand side. For part B, you can use the result of A, or you can do it other ways. For example, some students notice that x equal 2i. So that's also a very, very convenient way of calculating. The answer is -1, 0, 0, -1. For question 15, part A, the answer is 0 matrix. And part B, you're supposed to give an example. So on your homework, I wrote, find an example. So the example is an actual example. And a lot of students say, oh, this is an example. This is supposed to be a clue because part A is supposed to guide you to think about what the example is. So this is an example. And this is a clue. Why don't I accept this clue as an example? It's not entirely correct because you didn't specify what A and B the values of A and B are. Suppose A and B are 0, then it doesn't qualify as a counterexample. So I suppose an actual example should be better. In question 17, you are not supposed to write the answer directly. These are the answers. These are the answers. So you're supposed to find a diagonal matrix, find out all the diagonal matrix D, such that D squared equal this given matrix. Now, if we're talking about diagonal matrix only, you will find out that A squared equal 4 and B squared equal 9. So these 4 are the only answers for this question. But you can imagine if we extend our constraints. Let's say we do not require a diagonal matrix. Then I don't think the answers are these 4 only. Do you know what I mean? So for diagonal matrix, these are the only answers. So these are all the steps I think you need to show. For question 8, some of you, this one is easy. You need to compare both sides. And for question 24, part A also, this part is like a clue. You must think of something and then something square equal 1, 0, 0, 1. And then you can find these ones. For part B, you can use the result of A and consider different values of A, and get a few different square roots. Now here we borrow the concept of square roots from the real numbers. We can also talk about the square roots of matrix, and you can see there are many. There are many. Not only 3, there are infinitely many. That's also something special about matrix, isn't it? So if you have any question, let me know about the homework. Now let's talk about this lesson, determinants. Now, before we go into the definition, I think that let's spend a few minutes talking about the whole picture, the whole idea of why the lessons are arranged this way. Now, why do we have to study determinants now? As we progress, you may remember we discussed addition, subtraction, multiplication, scalar multiplication first, and then multiplication. And then last lesson, we discussed the very simple one, not very simple, but very straightforward. It's called transpose. Now you may think that, oh, maybe this is time to talk about the division of matrix. Now you are right. We're moving that direction. We're moving. Just something extra before I move on. It's another problem. Now in your homework, sometimes I see students want to express 1/2 times A. And some of you wrote A divided by 2. A is a matrix. I don't think this is allowed. Do not write this. Only write this. This is wrong. This is correct. This is just how you write it. This is a matrix multiply a number, scalar multiplication. And this is not a division. This is a multiplication. Technically, we have not talked about division of a matrix yet. So back to this, determinants. I think this is the final thing we have to talk about before we move on to the division of matrix, the determinants. But let's talk about why. I'll give you a very clue. You know that when we solve an equation, and these are numbers, a times x equal b, and these are numbers, and here I use scalars. Scalars means numbers. Is there definitely a solution? Because we know this equation so well, we know that when a is not 0, this equation has a solution that is b over a. And we know that so well. This equation is very simple. As long as a is not 0, I can always find a solution. But when a is 0, and b is not 0, okay? B is also 0. B is also 0. And then you will see that x can be anything. So we have conclusion that it has infinitely many solutions. And we should add another sentence to conclude this discussion. That is when A, I don't know why it's missing. When A is equal to 0 and B is not equal to 0, this equation has no solution. Okay, because the left-hand side will be 0, no matter what x is. The left-hand side is 0 and the right-hand side is not 0. So, although most of the time we talk about the first scenario, but the other two scenario also happens. What I want to say about this equation is that when we want to divide A to get a solution, we always want to make sure that A is good. Now here good means A is non-zero. Okay. The same thing happens with X, with matrix. We're not doing it now, but we will be doing this in the future. Is that in an equation like this, where this is a matrix and this is another matrix. So this times X equal to another matrix. Now, how do I divide? Now, how do I divide the matrix and get a solution for X? It really highly depends on whether or not this value is good. Now, if this value is this matrix, if this matrix has a similar characteristic as 0, we will say, oh, this one I cannot divide. Now, if this one is similar to a regular number that is non-zero, then we say, oh, it can be divided. So this thing, now later on we will talk about this in the next chapter. So right now you must know that this coefficient in front of X, this value, this matrix, will affect the solution. It will affect the division that we do now regarding matrix. So right now, we need to find the quality or the characteristic of the matrix, which we call determinants. Determinant. In other words, we will find something to determine whether or not this matrix is good enough. So we can move on to do the division. At least this is how I understand it. So it's very strange that in the middle of this chapter, in which we should really dive into studying matrix, and we will not. This 10.3, we will not be discussing matrix anymore. We will be discussing the determinant of matrix. And this determinant is a quality of a matrix. Look at the notation. Look at the notation. A is a square matrix. Now we only discuss square matrix because other matrices, it's too difficult to define the quality. For square matrix, it's easier to define the determinant. So square matrix, just change it a little bit. I will change this thing, the large bracket, into the absolute value sign. Just this time, it doesn't mean absolute value. And this notation means the determinant of the matrix. Now you can do it simpler, or you can write this. It looks like the absolute value of A, but it's not. This is the determinant of A. Or you can write DETA. DETA. They all mean, the three of them, they all mean the determinant of A. Okay, I think especially this one. This one, you just change it a little bit. This one has a little curve, and this one does not have curve. And that means determinant. and this one is a matrix. Now, for this one, if A is a 1 by 1 matrix, then the determinant of A is equal to DETA is equal to this matrix, and then put the absolute value sign in it, and it is defined as this value itself. So I think for the 1 by 1 matrix, it's extremely confusing because this means the determinant of the matrix. It doesn't mean the absolute value of A. For example, look here. This matrix only has one element, that's -3, this matrix. Because you can see a bracket outside, that means this is a matrix, not a value, okay? So the determinant of B is the determinant of B. This is also the determinant of B, and it's equal to the value itself. Whereas the absolute value of -3 is 3. Now these two look exactly the same, so you must make sure that you understand the whole passage, the context, before you judge what this is. But I think it's very rare though, because we almost never talk about 1 by 1 matrix, okay? But that does exist. So for 1 by 1 matrix, it looks like absolute value, but it's not. Now for determinants of 2 by 2. This A is a 2 by 2 matrix. Now how do I calculate the determinant of A? This is the formula. Now this is seen, this is seen as a definition. You just have to memorize it, and then later on you know how to calculate. The memorization is from the principal diagonal. This is the principal diagonal. This one minus this one. The other diagonal is not the principal diagonal. The other diagonal is not. So it's A11, A22 minus A12 times A21. An example would be DETA equal 7, 5, 1, -1. Remember, this is not absolute value. It equal to principal diagonal minus the other one. And then you get a value. And this is the answer. Determinant of a matrix is a value. It can equal to any real number, basically. Part B. DETA equal DETB. That means -12 equal 3, -x, -8, 4. That means -12 equal 3 times 4 minus -x times -8. -12 equal 12 minus 8x. 8x equal 24. And x equals 3. This is just a simple practice. Okay. Now, right now, this definition looks very odd. You just need to bear in mind that this definition is based on a lot of theories, based on whether or not this matrix can do a division, in quotation, a division. So you will need further knowledge to understand the definition. But right now, the definition is a definition. You just have to treat it as any definition. You have to memorize it. Okay. That's for a 2 by 2 matrix. For a 3 by 3 matrix, the definition is different. We also have the notation first, DTA equal to the matrix determinant. And then you can see it's a lot more. It's a lot more. It's basically also starts with the principal diagonal. That's my first. This is my first term. So it starts with the principal diagonal. And then it's not just 2 terms. It has 6 terms. So I have to do the principal diagonal first. And the second value is parallel to the diagonal, but it's here. This is the second diagonal. Basically, it's like this. Come this way and go this way. So these 2 numbers times this number. It's parallel. It's parallel to the principal diagonal. And the third value is also parallel, which is from here and go up. These are the 3 positive terms. Let me repeat. The first value is the principal diagonal. The second value is this one, parallel, and then goes round. And the last one is this one, parallel, and go this round. So the 3 positive terms are these 3. Now for the last 3 terms, we are not going along the principal diagonal. We're going this way. This is this way. This is the first term. Is the other diagonal. The other diagonal. And then the other 2 is like this. Also parallel to this diagonal. And this one, the last term is this one, parallel to this diagonal. Is these 2 values multiply A33. Is that okay? That's how you memorize it. It has to have 6 terms. It's much more complicated than the 2 by 2. Now you can imagine 4 by 4 and 5 by 5. Those determinants are more difficult, but we will not be discussing those in our textbook. 3 by 3. That's the largest determinants we have to calculate. The definitions are also, they look very different, right? 2 by 2, 3 by 3. Let's do that. Evaluate the determinants of these 2 matrices. Three, 2, 1, 2, 1, 0, 0, 3, 5. For me, it's 3, 1, 5 plus 2, 0, 0 plus 1, 2, 3, and then minus 0, 1, 1 minus 2, 2, 5, and minus 3, 0, 3. Now check if you have the same answer as me. You go this way, and this way. That's the last 3, okay? And then you will have 6 terms. 15 plus 0 plus 6 minus 0 minus 20 and minus 3. And the answer is 1. another one, 1, 4, 0, negative 4, 2, 0, 0, negative 5, negative 3. This one is 1 times 2 times negative 3 plus negative 4, negative 5 times 0 plus 0 times 4 times 0 minus 0 times 2 times 0 minus 4 times negative 4 times negative 3 minus 1 times negative 5 times 0. Okay, and that is equal to negative 6 plus 0 plus 0 minus 0 minus 48 and then minus 0. The answer is negative 54. Is it fine? I do it faster than a lot of students, but the rule is simple. By the way, this rule, this definition is also called the Sarah's rule in the textbook, but you don't have to know that name. Don't have to know that name. This is, you have to just be patient. Okay, I figured that in this chapter, especially at this stage, you are told a lot of things. Now you're told, oh, this is what you do. And actually carrying out these steps is not difficult. It's just a lot of new things to remember. So try to grasp every little bit during the lesson. Moving on, another example. And this example is just for you to do another, this is another type of question, but just using the definition of 3 by 3 matrix, determinants of 3 by 3. So for this one, I'll go from the principal diagonal. That is 2 times 0 times negative 3 plus negative 2 times 1 times x plus 1 plus 3 times negative x times 1 minus the other side, which is 3 times 0 times x plus 1 minus this one is minus 2 times minus x times minus 3 and minus 2 times 1 times 1. This is the determinant and it's equal to negative 3. And then I just have to solve a simple equation, which is 0 minus 2 x plus 1 minus 3x minus 0 plus 6x minus 2 equal minus 3. And then we have negative 2x, negative 2, negative 3x plus 6x minus 2 equal minus 3. And we have negative 11, positive x equal negative 3 plus 2 and x equal 1. Okay. The questions, it's quite straightforward. As long as you know the definition, you can solve it. Now bear in mind, we're not applying the determinants yet, because we don't fully understand what's the usage, what is the actual use of the determinants yet. We know that it's going to help us find how to divide a matrix, but so far we do not do that yet. So this is just straightforward practice. So far, any question? Before we move on, you must make sure you have no trouble understanding the notation of matrix. The notation. You must have no trouble understanding 1-by-1 matrix determinant, which looks very weird, because it can be negative. It looks like absolute value, but it can be negative. And you must understand how to calculate 2-by-2 and 3-by-3. This formula, you have to memorize it today and right now. Okay, take a deep breath. After this, we're moving on, and it's difficult to guess what we're gonna learn next, but I can tell you that it's something about the determinants. This part we're going to discuss some properties of the determinants, but we will start with introducing new concepts. Now, after this concept, we'll discuss the properties. This concept, a minor and a cofactor of a determinant. What does that mean? Now this thing, this is determinant of A, this is a determinant. This huge thing is a determinant. Remember determinant is, we were always talking about square matrix. So you can see the last value here is A and N. It's M by M matrix. So what is a minor? A minor we call M. M is a minor. M is a minor. It's, how do we find the minor? Now first we find Aij. And then we delete the ith row. And then we delete the jth column. Now it's difficult to see it here, but I'll give you a lot of examples so you understand what it is. This is a 2-by-2 matrix, and this is the determinant. So this determinant. Now, what is the minor of A11, which is M11, 11, sorry, mistake here, 11. A11, minor M11. It means I take this matrix and I delete the first row, and I also delete the first column. And this is what I have, -9. And the remaining is another determinant. This is not matrix. Sorry, this is not absolute value. This is the determinant. I call -9. Okay. Now the other minor, the minor of A12. Now A12 is this value. This is A12. So in order to get the minor of A12, I will delete the first row, A12. Sorry, A12 is this one. Sorry. A12 is this value. So in order to get A12, I will delete the first row and the second column. Basically, the row and the column, this element is in. So delete a first column, the first row, the second column, and then I have another matrix, which is 5. Third example, how about the minor of A21? Now first you find A21, this is A21, and then you delete, and then delete. You will get a remaining matrix, a remaining determinant. The last one is A22. The minor of A22. The notation is M22. The notation is M22. And that is to delete the second row and the second column. And then you get a matrix determinant. That's 3. Okay. Now, how about another example, a 3 by 3 matrix, the determinant? How do I find the minor of A22? And first, I find A22. Okay, this is A22. The minor of A22 is M22, and then you delete the second row, you delete the second column, and you're left with another matrix, another determinant. That's 1, 3, 7, 9. And then you need to calculate, which is 9 minus 21. That's equal -12. Okay. The last example. How about the minor of A32? The minor of A32, I will find A32, and then I will delete, and then I will have a 2 by 2. And then I'll do a calculation. And the answer is -3. Is it fine? So a minor is a smaller determinant. By smaller, I don't mean the value is smaller. I mean the size is smaller. Okay. For the determinant of order 2, the minors are all determinants of order 1. For the determinant of order 3, all the minors, there are 9 minors, because for each individual element, you can find its own minor. All the minors of determinant of order 3, they are determinants of order 2. Is it fine? Again, this is just new things. The meaning behind these is unknown yet. We don't know why we need to find the minor. We just know that this is how we find the minor. But later on, it will be reviewed to you what the use is. So to find the minor, Mij, that's the minor. Okay? Are you fine? If you're fine, you should be able to answer me what is the minor of M23 for this matrix, for this determinant. What is the minor of M23? M23. You tell me a value. Now, what is the minor of M23? Chen-Hei?
-6.
Correct. Okay. That's it. That's it. Minor. Just after minor, let's talk about a cofactor. A cofactor, which we call C. Minor is M, cofactor is C. C, cofactor, is almost defined as equal to minor. You see, cofactor and minor are almost equal, except that I need to multiply something by the minor. Okay, and the something is -1 to the power something. So basically, I have the minor, and then I'm going to add a negative sign. Sometimes I will add a negative sign, depending what I and j are. What does that mean? That means this value, the cofactor of A11, which is called C11, okay? It's almost equal to M11, but I need to add -1 to the power 1 plus 1 in front of M11. Now, in the previous question, we got that M11 is -9. So I have -1 to the power 2 times -9. So the answer is still -9. Okay. Now for this element, A11, the cofactor and the minor are equal because the value I add in front is a positive sign. Now for cofactor A12, this is C12. It's almost equal to M12. But I need to add a negative sign in front of M12. Now previously I already know M12 is 5. So this one will be -5. The next one, the cofactor C21 is equal to -1 to the power 2 plus 1 M21. So this is not exactly equal to M21. This is equal to the negative of M21, which is 2. The last one, this is C22, which is equal to -1 to the power 2 plus 2 M22, and that is equal to -1 to the power 4 times 3, and that is 3. Okay, so for the cofactors, they are equal to the minus, but we are adding a sign. And the sign is determined by basically the position of the element. If the position of the element is here, I will just say, oh, it's here, it's a plus. If it's here, it's a minus. So for the cofactors of 2 by 2, we know that the 2 by 2, the cofactors, the signs are positive, negative, negative, positive, if you know what I mean. The position will decide the sign. Now for 3 by 3, it's similar. For 3 by 3, this is an example I just took from the textbook. For this one, C11 is still equal to M11. This is just M11. Do you see? C11 is M11 because I delete and delete, I get M11. And I don't need to add a negative sign in front. But for C12, this is M12, but I need to add a negative sign in front. So C12 is negative M12. Now C13, it's flipped again because 1 plus 3 is 4. And that means I do not to add a negative sign. So C13 equal M13. Okay, and so on and so on. Now for 3 by 3 matrix determinant, the cofactors are positive, negative, positive, negative, positive, negative, positive, negative, positive, like that. Now here the signs mean that it's equal to the minor or it's opposite to the minor. Again, we're not talking about how to use it. We're talking about what it is. The minors and the cofactors, they're very close and very similar definition. And later on, we'll find the usage of it. Now, before that, let's practice. For determinant A, can we find the minor and the cofactor of 7, which is this value, 7? And the minor, I will do the deletion and deletion, the minor, which we call M23, the minor. That is equal to 2, 5, negative 1, 3, and that is 6 minus 5, that's 11. So this is the minor. Now the cofactor C23 is equal to negative M23, which is negative 11. Okay. Now for the element negative 1, let's find negative 1 here. So I'll do a deletion. So for the negative 1, the minor is M31, which is equal to 5847. That's 32. Oh, sorry, 35 minus 32. And the answer is 3. And for the cofactor, which is C31, that is equal to negative M31. And that is equal to, well, not negative, positive, positive M31, which is equal to 3. So that's how you get it. Now, to find the cofactor, I always find the minor first, and then I decide whether or not I flip it to add a negative sign. Now you can do the practice and let me know when you are done. Okay. I guess you're all fine. You must be fine, because if you're not, then we cannot move on. Okay. So now we know what the cofactors, what the minus are. As I said, I mentioned before, the next we must go on to talk about the property of determinants. So on the next page, this part is called the expansion of determinants by cofactors. Now this is this is what I call a property, because according to the definition, we already know how to calculate a determinant, right? But there's another way called the expansion. Another way called expansion. And the expansion is supposed to reveal something new to us. Okay, let's read it. Now for a 3 by 3 matrix, which is also true for other matrix, but here we only talk about the 3 by 3. For other ones, also the same. We can expand the determinant by a row. This is expansion according to the first row. which is every element in the first row multiply its own cofactor. A11 times C11 plus A12 times C12 plus A13 times C13. And that is called an expansion. This itself, the first line of this is called an expansion. Now we have different expansion. We don't have to expand according to the first row. We can expand according to the second row, which is this one. So the determinants is equal to the second row multiply their own respective cofactor. A21, C21, A22, C22, A23, C23. Now you can imagine I can do it to the third row. I can also do it to the first column. Now this is the first column, do you see? A11, A21, A31, that's the first column, and the second column and the third column. Basically, we are saying that you can decide. You don't have to do it, find the determinants by definition, which is 6 terms. You can do it using 3 terms as long as you expand it according to a certain row or column. Now I'll show you how. We evaluate determinant A by expanding along the third row, which is this one. The third row, I will use the 3 value, -3 and 0 and 2. I will write down the cofactors. The cofactors are, the first one is, let me delete, that's 1, 3, 0, 2. Remember I add this is the cofactor. The second cofactor is this one, which is 2, 4, 3, -1. Now here I already add a negative sign in front, so this is the cofactor, not the minor. And then the last element is 2. I'll delete this and this. I'll get 2, 1, 4, -2. Okay, and then I'll just calculate and get the answer. This is 2, and this is 0. So this is not 0, but this is 0. The whole thing is 0, so I don't have to calculate the second term. The last term is -4 minus 4, that's -8. So the answer is -6 minus 16, -22. Can we see that? -6 minus negative. Why is it -31? Is it not correct? C31 is wrong. 3-1 is wrong. 3-1 is wrong. This one is wrong. Sorry. C31 is wrong. It's 1, 3, -2, -1. -1 plus 6, that's 5. Yes. So the first cofactor is wrong. So this answer is -31. Okay. That's okay. This is part A. The answer is -31. The second part, expand according to the second column, which is this one. I will do 1, -2, and 0. So you can see 1. This is 1. Here, this is 1. This is -2. And this is 0. So you can see the 3 elements there. And I also need the cofactor of each individual element. So the first one, I will delete and get 4, -1, -3, 2. For the second one, I will delete and delete. I get 2, 3, -3, 2. And for the last one, I will do 2, 3, 4, -1. Okay. And the signs are already adjusted because I get negative and positive. This is a positive and negative. So these are the cofactors, not the minus. And then you calculate, you will get 11. Well, not 11. 5. Oh, 5. And the second one is 13. And the answer is also -31. Okay. It's interesting, isn't it? Oh. It's interesting because first of all, we're not satisfied with the definition, although the definition is not entirely outrageously difficult. It has 6 terms, but it's not like the end of the world. It's still okay. But we're unsatisfied with it for some reason. And the second reason I hope that you all wonder is that how on earth are we allowed to do the expansion according to different rows or columns and still get the same answer? So you can see that for this example, I expanded according to the third row and according to the second column, and the answer is the same. This, in our design of the lesson, is trying to convince you that this is correct. But in fact, you can imagine it's difficult to absorb and it's difficult to understand. It's difficult. I think anybody is difficult to be convinced that, oh, no matter how you expand it, you always get the same answer. But however, the proof is in the textbook. Let me find the proof. In the textbook, this is the proof in the textbook. Say that the proof, you see, in the textbook on page 39, after this blue part, which is an investigation, and then you can find, oh, they do get the same answer. You can do that on your own, and we'll already have done that sort of. And this part is to say that, oh, the determinant can be basically expanded according to the first row. This is according to the first row. And this part is the proof. Basically, it's exactly just pure expansion. Pure expansion. You will find that according to this expansion, you will get 6 terms as well. And the 6 terms are identical to the 6 terms from the definition. They're not in the correct order. For example, this is plus, minus, plus, minus, plus, minus. But in the definition, it's plus, 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 and then minus, minus, minus. But anyway, there are 6 identical terms according to the first row. Now you can do this repeatedly, so you can get that in any expansion, not just the first row, the second row, the third row, the first column, the second column, the third column. You always get 6 terms of the same expansion. And that is supposed to be a proof. But I think you can guess that the knowledge behind this is really a huge amount of knowledge, because it's not so easy to discover. anyone who found this must be genius, must be very, very smart. So they found, oh, I can do this instead of doing the expansion. Yes, yes. Right now, we must note that we're standing on the shoulders of a lot of clever people, and they discover this, and it's not easy to discover. This knowledge is based on deep, deep understanding of matrix, and then they develop both the definition and the property. Now, in my days, I must tell you that in my days, when I learned this part, my teacher used this part. I call in our textbook, this part is called the property of determinants. They use this as the definition and use the definition as property. I think it goes both ways. If you think this is the definition, then this is the property. Previously on this page, this is the property. If you think this is the definition, then the expansion is the property. Now, either way, it's not easier either way. But anyway, it's a huge fact that the expansion is real. Now, the textbook doesn't talk about the expansion of 2 by 2, but it's also true because if you have a 2 by 2 matrix, you can do expansion according to the first row, which is A11, C11 plus A21, C21. That's also correct. You can also expand it A12, C12, A22, C22. You can do it either according to the row, according to the column, which is A11, C11 plus A12, C12, or A21, C21 plus A22, C22. These are rows, these are columns. It's also true. Okay. So the property. In the textbook, it's sort of like it's proved. Because it's the first one is proved, we can imagine the other 5 are also proved. But the proof doesn't review anything though. It doesn't review how this is obtained because you don't go and then prove something that you don't even understand. The understanding, I think, comes afterwards. Okay. And then let's talk about the example. This example, expanding along the second row, I'll do that. The second row, this is the second row. Expanding the second row. So it's 0, M, B, and D. And then 1, A, B, C, D. And then 0, A, M, C, N. Okay. Now the signs are already added. You can see this is negative plus negative. So that means cofactor because the cofactors are negative plus negative. And this answer. Now the reason I expanded according to the second row is that the first value and the last value are both 0. So I only need to calculate the middle one, which is AD minus BC. And then it's done. You can see, I think it's somewhat simpler if you have a lot of zeros in that row. Okay, and in this case, there are 2 zeros in this row, so I only have to calculate 1 co-minor, and that's it. If I expand it along the third column, which is this, so I have B, which is 0, 1, Cn, and then 0, which is AMCN, and which is DAM01. Okay, so this one is negative C, and this one is A. It's still equal to minus BC plus AD. Same answer. Same answer. Now, expansion according to the third column is less easy, less easy than the first expansion, but still. I also want to remind you that you always get the same answer. For the quick practice, it's actual values, so you can do it and tell me when you're done. Okay. I think the signs, because in the textbook, in the notes, I typed out the signs for you. So you don't have to decide the signs yet. But in your homework, you'll be deciding what is the plus or minus for the cofactors. Okay. And you can see that for the second expansion, it's much easier. Even if you get these two wrong, it's still fine. As long as you get this correctly, then you get the correct answer. Next, basic properties. Now these ones, some of them are easy, some of them are difficult. But these are true for both order 2 or order 3 matrices. I'm going to tell you that these are true for order 4 and order 5, order 6, but that's beyond our syllabus. So determinant of 0 matrix is 0. That is because you can see have 0, 0, 0, 0. And that is 0 minus 0, that's 0. For 2 by 2, it's very obvious. For 3 by 3, I suppose so. Now for identity matrix, it's 1, 0, 0, 1. That is 1 minus 0 equal 1. It's also true for identity matrix. Okay. A transpose is equal to, I correct myself. It's the determinant of A transpose is equal to the determinant of A. This is also true. For example, A, B, C, D, it's equal to AD minus BC. If you transpose, that is A, B, C, D this way, it's also equal to AD minus BC. Now here I'm using this matrix of order 2, the determinants of order 2, but for order 3, it's also true. It's also true. So that transpose does not change the determinant. The second last one is the scalar multiplication. Now, scalar multiplication, if you multiply A, that is K times A, B, C, D, basically, this is K times a matrix, not K times a determinant. K times a matrix equal to KA, KB, KC, KD. Okay? And then if you're using the determinant KA, KB, KC, KD, you will see that it's KA, KD minus KC, KD, which is equal to K square AD minus K square C, BC. No. BC, which is equal to K square AD minus BC. So from this example, this actually is a proof for 2 by 2. From the 2 by 2 example, you can see that after the scalar multiplication of a matrix, the determinants are changed. The determinants changed. It's changed to another factor is added in front, which is K squared times the original determinant. This is the original determinant, AD minus BC. Now you have a K squared in front. Now for determinants of order 2, the K squared is added. For determinants of order 3, K cubed is added. Simply because every term has a K in it. Because if you multiply a scalar to the matrix, every term has K. So the final result will have K squared or K cubed in it, depending on the order. Okay, I think so far so good, except for the last one. The last one, remember A and B are both square matrix. They are both square matrix. So we say that determinant of A times B is equal to the determinant A times the determinant of B. Now I don't have a very good reason to tell you. We don't have a proof, but it's true. It's true. In the textbook, the proof will be too long. In the textbook, it says that the proof of the last one is in the appendix of the textbook, which is towards the end of the chapter. But even the appendix only explained the order 2. Now it says that in the textbook, the property of E for order 2 is given in the appendix. You can imagine it's a lot of expansion, and then finally it's verified. But the proof of E for n equals 3 is not included. It's just very long, just very, very long. But is it true? So the textbook says, let's verify it using an example. Now you can see an example. Now this is 3 by 3. This is also 3 by 3. This is A times B, also a 3 by 3. And you can see that the determinant of this, -27, is equal to determinant of A multiplied to determinant of B. Now this is a more profound result. You cannot just say, this is so obvious. It's not obvious. It's very hidden, but it's still true. Still true. One of the other property we learned in the past is this one, which is, I think, last lesson, the transpose. In the transpose, we're proven that A, B transpose equal B transpose, A transpose. That is already not very obvious, but this one is, in comparison to the determinant, if you say, oh, the determinant. Because you can imagine that A times B can be very different from A or B. Because all the rows and columns, they intertwine with each other. However, the determinant is still equal to A times B. Okay? No, you have to trust. Otherwise, we cannot move on. Is there a simpler way of proving it? I don't think so. I don't think so. Unless I'm not well informed. But I'm looking for a simpler way. Let me know if you know, because nowadays the people are clever online. They may know a simpler way of proving even 3 by 3. 4 by 4 is also real. 4 by 4 is real, but it's difficult to prove. Even 3 by 3. How to prove A, B determinant equal determinant A times determinant B. But we will just be using it. This example, can you find determinant B if you know this equation? Just don't have to, this is given and then find it. I'll just be using the properties. Because this matrix equals this matrix, I know that determinant of B, B, T, B is equal to determinant of negative I. So that I will have determinant B, T, determinant B equal. This is a K that is negative 1 to the power 2 determinant of I. And then we have determinant of B cubed, because all three are determinant of B on the left. On the right, you have 1. That's how I found determinant B is equal to 1 itself. You do it. You do it. This is a 3 by 3 matrix. You do it. You're given determinant of Q. Can you find determinant of P? Quickly. Let me know when you're done. Okay. This is a very short question. You will use this equation. You will get determinant PTP equal determinant of Q. And PTP is determinant of PT, determinant of P equal 36. And that will give you determinant of P squared equal 36. And this, remember, we're not dealing with matrix anymore. These are all values. The left-hand side is a value, the right-hand side is value, so I can solve the equation. I found that determinant of P is equal to 6 or negative 6. Next example. In this example, I will evaluate determinant of A minus 2I. Now remember that addition and subtraction cannot be split with determinant, so I actually have to find A minus 2I first, which is, for me, it's 4 minus 4, 1, 0, minus 2, 1, 0, 2, and that is equal to 2, negative 4, 1, negative 2. Okay, after find out, I will determinant A minus 2I equal 2, negative 4, 1, negative 2, determinant And then I get 2, -2, -1, -4. And the answer is -4 plus 4 equals 0. Okay. Now for this one, I can never split. It's not like A minus B is equal to determinant A minus determinant B. That's not true. For addition, you cannot split. Now, for part B, since we know that determinant of A squared minus 4i is equal to determinant of A plus 2i and A minus 2i. Now I can do a factorization, a so-called factorization, so that is a factorization, and then I can split it. For multiplication, I can split it. And then without knowing this determinant, I will know the second determinant. That's why I can conclude that this is 0 without even knowing what the matrices is. Okay, now for you, the factorization is real. It's real. Although it's not I squared. You will say, oh, this should be I squared, but I squared equal I. That's new. This is I, but also it's A squared minus 4i squared. So that's a factorization. And the second part, I think you can do the same. So determinant A cubed minus 8i, that is determinant A minus 2i times determinant A squared plus 2a plus 4i. That's an expansion, right? And then because this is 0, so that the whole thing is 0. Although the second factor may not be 0, but it's 0. In the end, it's 0. Okay. Now part C is similar. Part C is similar. It's just more factorization. So I'll just do the factorization part. So part C, the answer is 0. So the factorization part is a to the power 6 minus 64i. It's equal to a6 minus 64i6. And that is a cubed plus 4i cubed and a cubed minus 4i cubed. Is it 4 or 6? 6i. Yes. Okay. And then this one, I will factorize this one. This one I will keep. This one I will factorize as sorry, 64 is cubed, right? Okay. 64. What is the 4? It's 8, sorry. 8. 8. I was like, oh my god. 8. And then I don't have to do it anymore. I don't have to further factorize. That is a cubed plus 8i and a cubed minus 8i. Okay. And from part B, we already know this one is 0. That's why the determinant of this is still 0. Now you will do the practice and let me know when you're done. It's just the last practice. Okay, I see that you're completing. So this is the answer. For the addition, you have to do it yourself and then calculate the determinant. Once you get the determinant is 0, for part B, you can do a factorization and then it's 0. For part C, you can do a factorization. The factorization, like I said, is new. But since AI equal IA, for the most factorization in the past, we say, oh, this cannot be expanded anymore. That's because AB is not equal to BA. But because AI is equal to IA, this can be factorized. Therefore, you can get the answer. Now for the part C, this is how you factorize. You have to use a cubic, what do you call it? A cubic, the sum of cubics. The sum of cubics. That's all. Okay. That's all for today. I'll see you in September. Bye-bye.